So as we have seen, for every conservative force, there exists a corresponding potential energy. Now, when it comes to physics 8A, we have two common cases of conservative force. We have seen both of them. One is the gravitational force. The other is the elastic force of an ideal spring. So let's now find the expression for the corresponding potential energy for each one of them. So the first example is the gravitational potential energy. Now we have this basketball starting from a certain initial position I, it ends up in a final position F. Okay, we can establish a y coordinate system going directly upwards from a certain reference level. It could be the ground, could be anywhere else. And we wish to calculate the work done by gravity from initial to final in order to find the expression for the gravitational potential energy. Okay, to do so, let's first recall how we define potential energy. The potential energy is defined so that W initial to final equals to U initial minus U final. Okay, this W is the work done by the corresponding conservative force. So that's a conservative force. Okay, so let's see, in our case, we know how to calculate the gravitational potential, the work done by gravity from initial to final position. Let's say it starts out from the initial position and went downwards by distance h. Okay, so this distance is h. As you can see in this diagram, it actually went downwards. Then the work done is just mgh. M is the mass, right? So we have here mgh. Mgh equals to U initial minus U final. Now, what I want to do is to rewrite H to express in terms of Y initial and Y final so that I can get U as a function of Y, right? And so I can plug that into the expression for mgh, then I get mg y initial minus y final equals to u initial minus u final. Okay, I'm going to work out this mgy initial minus mgy final equals u initial minus u final, right? So at this point, if I ask you, what is the expression of the gravitational potential energy U as a function of M, G, and Y, you probably would just tell me, I found it, right? This is Y initial, it has to do with U initial, and this is Y final, has to do with U final. So naturally you would say, oh, the expression of U, G, so I'm going to use a specific subscript G for gravity as a function of Y. That is just equal to mgy, right? Mgy. Well, is that right? Well, certainly there's nothing wrong with that. This certainly is a valid expression for the gravitational potential energy. However, there's something that I have to make sure you realize. The initial definition of the gravitational potential energy, or any potential energy for that matter, is defined as a difference, U initial minus U final. We have never defined U initial or U final separately, okay? The only thing that's clearly defined is the difference between U initial and U final. So therefore, that leaves us some flexibility. As long as you find an expression for U such that U initial minus U final equals to the work done, then it's valid. What that means is that we're not really limited to this expression of mgy. We can add a constant. We can add a constant to mgy. Okay, I'm gonna highlight it with a red color. Why is that? Because if you add a constant to U initial and add a constant to U final, then when you take U initial minus U final, what happens to that constant? Well, it cancels out, right? It becomes zero as long as it's a every term to the expression of any potential energy, as long as there's the same constant for both the initial and the final. In the case of gravity, what that means is that by adjusting that constant, I can reset the zero of the potential energy to be anywhere I want. For example, in this particular coordinate system, if I choose the constant to be zero, then I'm basically saying that when y equals zero, then ug of y is also equal to zero. So therefore the origin, or therefore the 0 point of the gravitational potential energy is set to be here, right here at the origin of the coordinate system, okay? You can call this the street level. You say the street level is with potential energy defined to be zero. But it doesn't have to be the case. I mean, you can define as, you know, the gravitational potential energy to be zero here, somewhere above the street level. Let's say here, you know, the second story, for example. Then, you know, you can do so by adding a negative constant, such that when y equals to the value of the second story height, which is right here, ug of y happens to be zero. You can do that. Okay, that's not a problem as long as you use the same constant for ug throughout the rest of the formula for the same problem, so that the difference of initial minus u final would be the same as mgh. So you define this point as a 0 point. If you do so, then every point below that would have a negative potential energy. Every point above that would have a positive potential energy. So that's allowed. Okay, and so once again, you can define the zero of the gravitational potential energy to be anywhere you want by adjusting the constant, and that is totally allowed. Okay, so this is the expression for the gravitational potential energy. It's just mgy plus a constant. So let me box that. All right. Now I didn't calculate the integral of the work done by gravity. I mean, I already did that in a previous chapter. So you know, we just accept it as mgh, and it doesn't matter how it gets there, right? You can take any path you want to go from initial to final. Okay, you can take a path like this. You can take a path like that. It doesn't matter as long as you get there. The work done is the same. Okay, this is something we have already seen in a previous chapter, so I'm not going to repeat it here. If you cannot if you cannot recall that, just go back to chapter 7, see how we calculate the work done by gravity. You will see that. Now let's look at the second example of the potential energy associated with a conservative force, and that is the elastic force of a spring. Okay, so in the case of elastic force, I have an ideal spring of spring constant K, and I set the coordinate system to be along the direction of stretch or compression of the spring. We call it X. At the origin is right here at meaning that it doesn't have either stretch nor compression. For spring as a function of X. We have seen that in the previous chapter, and the answer is Fs equals to negative Kx. This negative sign is important because it tells us the direction of the force is always against the deformation of the spring. If X is positive, that means the spring is getting stretched. Then F is negative, meaning F is opposite to the positive direction of X. So the force of the spring is to try to pull the spring back to make it shorter, or back towards the original length. And if X is negative, that means the spring is getting compressed, and then Fs becomes positive, which means, again, the force of the spring points towards the equilibrium position at X equal to 0. So either way, the spring tries to restore its length to its original value at equilibrium, upon which the tip of the spring is at X equal to 0. Okay, that's what we call a restoring force, or more precisely, linear restoring force, because F is a linear function of X. That is the case for the ideal spring is known as Hooke's law, as we have said before. Now, this is a conservative force. As long as we restrict the motion along this one dimension x, it's a conservative force. How do we know it's a conservative force? Because if you take any round trip, okay, any round trip, if you stretch the spring, it does, the spring does a negative amount of work if you try to pull the spring and make it longer. But then as the spring gets back to the original length, the force of the spring does positive work, okay? And these two works cancel out. They both have the same magnitude of 1/2 kx squared, except one is positive, the other is negative. The total work done is 0 as the spring gets back to its original length. So for a loop, the work done by the spring is 0, and therefore it is a conservative force. Now, how much is the associated potential energy for this spring? Any way we want. Let's say we start from the origin. We start from the origin right here. So this is my initial position. And we end up somewhere here, we call it final position. And the distance is x from, the coordinate of this point is x. Okay, so the spring has been stretched by an amount x at the end. Okay, I'm going to apply the definition of potential energy to find its expression. So again, let me write down the expression, the definition for potential energy, and it's like this. Again, U initial minus U final equals the work done, initial to final. Okay, now let's be a little bit more careful here. I'm not going to just repeat, the calculation we did before, 1/2 kx squared. I don't just want to tell you what the answer is. You already know what the answer is, 1/2 kx squared. I'm going to do a more careful calculation to evaluate this integral more, from scratch, so we can make sure we understand for works. Okay, you don't have to get stretched, and you can also compress it. It's the same thing, but just this is one possibility. In doing so, as I pull the spring from initial to final, I'm moving along the along the negative x direction, right? Because it doesn't want the spring to get stretched. It is a restoring force, so it goes backwards. And therefore, the displacement and the force are opposite to each other in direction. Therefore, the work done by the spring is negative, which means U final will be greater than U initial because the work done, W initial to final, is negative. Okay, but how much is it negative? Well, we'll have to figure out the actual expression for the work. So let's do that. The work done from initial to final, Fs, it's a vector, Fs, dot dr. Dr is actually dx in this case. All right, so I'm going to use x as a variable now. It starts at x equal to 0. It ends up at the final value x. The magnitude of the force from the spring is kx. We know x is positive throughout the entire trip. In this particular case, from initial to final, is always positive. But the direction of the force is along the negative x direction, so it's negative I. Okay, I'm going to put in negative I, so you know the direction. Okay, and then dot dr. Dr, the magnitude of dr is dx, and the direction is along I. Okay, so the direction of dr is along the positive x direction. Now, let's work out the I dot I. The I dot I, of course, gives you 1. There's a negative sign coming out, so minus 0 to x, okay, kx dx, right? And that's easy enough to work out. This is just negative 1/2 kx squared. So indeed, the initial potential energy is less than a final potential energy. By how much? By 1/2 kx squared. Now, I can define the initial energy to be 0 Why can I do that? Because I have the flexibility to add a constant to the potential energies, right? For any potential energy, not just gravitational potential energy. And this also means I can set the potential energy to be 0 anywhere I want. So why don't I just set U initial to be 0, which actually is a reasonable thing to do, because at initial position the spring is neither stretched nor compressed. The elastic force is not engaged, so might as well call that the 0 point of potential energy. Okay, you don't have to do that, but that's usually what people do because it makes sense. Then I get negative U final equals negative 1/2 kx squared. Okay, U final is the potential energy at a certain amount of stretch of x. So U final is just U of x. Okay, it's just U of x. I'm going to use E for elastic potential energy. And what is that equal to? 1/2 k x squared. Okay, so this is the expression for the elastic potential energy, with the origin set, with the 0 point set at the equilibrium position of the spring where x equals 0. Okay, so this is the second of these two examples, and usually we're limited to these two cases when it comes to elastic, when it comes to potential energy in physics 8a. You're going to see more examples like electric potential energy later in different parts of physics 8 series. But these are the two examples we see in 8a. Okay, now there is a big difference between this expression, UE, and the one before that, UG. UG, as you can see here, is a linear function of y, and this y can be positive and negative. Now, if you plot UG as a function of y, you find it's just a straight line. There's no upper limit, there's no lower limit. Okay, whereas in the second case, you have a potential energy which is always positive, assuming that the potential energy is 0 at equilibrium. So this marks an important difference between these two potential energies. In fact, if I had to plot it, this is what I get. Okay, if I were to plot the gravitational potential energy, I'm going to get something like this. Okay, this is y, and this is this is y, and this is UG as a function of y. Okay, whereas with elastic potential energy, if you plot it, it looks different. It's a parabola with a bottom. I'll try to draw a straight line here. Okay, there we go. It's a parabola with a bottom. So it looks like this. Okay, I didn't draw it very well. Let me try this again. You get the idea. Okay, so this is U. This is U E x as a function of x. Why do I say there's a big difference between these two cases? Because in the first example, there is no lower limit. There is no minimum. Okay, this guy has no minimum. This guy, on the other hand, has a minimum. Right here, this is the minimum right here. Why is it important to have a minimum? You ever wonder why things move the way they do? Why do an object settle at a certain place, it doesn't want to move anymore? If you drop a stone, it keeps on going downwards until it hits the hard ground. If there's no hard ground, it keeps on going downwards. Whereas if you put something in a bowl, okay, you put a bead in a bowl, the bead may move a little bit, but eventually it's going to settle at the bottom of the bowl, right? At the bottom of the bowl. Why is that? Because this is where the potential energy is the lowest. Okay, so when the potential energy has a minimum, this is where you're going to find the object eventually. Everything has a tendency to move towards the lower minimum of the potential energy. Okay, so in the case of a spring, let's say you attach a block to the spring and you pull the block away from equilibrium, then the block is going to start to oscillate, right? It's going to oscillate, and eventually, when all the oscillation stops, where's the block going to end? It's going to end at the equilibrium position of the spring, where the spring is neither stretched nor compressed. That's an example. That's another example of the system seeking the lowest potential energy. Okay. Whereas with gravity, there is no lower limit. Okay. So, an object under the influence of gravity will keep on moving until it hits the hot ground. It's got no place to go, then it stops. That is very important to realize. And you will see many other examples where a system, when it evolves, it eventually ends up moving towards the lowest point of gravity, of potential energy. Okay, so we're just seeing the first couple of examples. So in the next lecture, we're going to apply our knowledge of potential energy and the conservation of energy to start solving problems.